Good day, class. Today we want to talk about functions with different input arguments, and we want to see what will happen if we give a value as an input to the function, what will be the output. We will try to find the derivative of the function and the integral of the function, but this time we want to do it in a symbolic form. So let's get back to our MATLAB. And if you remember, in previous session we have learned a comment which was called sims. And sims means that we are about to define a symbol. We are to define a symbol. Let's define the x, y, and z, and then we can say that y is equal to cosine of x divided by x, and we can define, for instance, z is equal to x squared minus 2y. Now if we run this program, let's save it and let's call the as test 8, let's run it. If we run it, we will see that we have the symbols x, y, and z, and this is the definition for y and this is the definition for z. Now in order to see how we can evaluate a value, how we can give a value for one of these symbols in order to get the output of the other one, we can use a function which is called eval. So let's say f is equal to eval y, but in order to use this function, what are the symbols that we are using in y? X. So we have to give a value for x. Let's say that x is equal to pi. X is equal to pi, and we want to evaluate our function y. Let's also clear the screen and let's run it. If we do it, this is the value for f. So what it does, it calculates the cosine pi divided by pi. We already know that cosine pi will be -1, so -1 divided by pi, which you can easily see the value of the pi is 3.1416. So you just divide -1 divided by pi, we will get the same value. Now let's say we want to see what is the value. Let's call this one g is equal to eval z, and if we run it, we will get the value of f. So we know what is x, value of y has been calculated in here, and now I am putting the value of y what was calculated before, a value of x which was pi, and I'm calculating the value of z. Now so we have seen how we can evaluate a function by giving some input variable. Now assume we want to find the limit of a function. Now what I do, I am using a function in MATLAB which is called limit, and I say that, let's see, y and 5. Let me put the semicolon in here so we don't see it, and if I do it, it says that the limit is cosine 5 over 5. Or let's see what is the limit of z and 5, and it says that the limit is 25 minus 2 multiplied by cosine 5 divided by 5. So it calculates the value of the limits. So another thing is that here, as you can see, my x and y, they are all functions with symbols. So let's see how we can calculate the derivative of these type of functions. Before, we have seen how we can find the result of a derivative at a given point. So we're getting a number. Now we want to do it in symbolic form. In order to do that, it's pretty simple. We use a function called diff, and I write, let's say, diff y. And if I run it, you will see that it says that the cosine x divided by x, its derivative will be this. Now this is the first derivative, right? So let's call it d1, and assume I want to see the second derivative, and I call it d2, so it will be diff y, and 2. So I can write the order of the derivative in here, and the default, if I don't write anything, will be number 1. Now assume I have let's say also a and b, and I have w to be x multiplied by sine of 2a plus x multiplied by cosine of b. So I have w to be like that, and if I run it, this is what I have as my w. Let's comment this line. So x is not is a symbol. I want, as you can see, w has 3 variables inside here, and I want to find the results. Let's call it d3, the derivative. So diff of w with respect to x. So if I write it in this form, it says that find the derivative of w with respect to x, which will be sine 2a plus cosine b, which as what we were expecting to see. We can define, let's call it even dA, so we can define, oh, it was dx, we can define dA to be the derivative of w with respect to a or b. And if I run it, I say that with respect to a, if I find the derivative, this term is 0, and this term will be 2x cosine 2a. Or you can calculate the dB, and it will be diff w and b, and the result, as you were expecting to see, is minus x multiplied by sine b. Now let's see how I can calculate the second derivative of this type of multivariable functions. In order to do that, I can, for instance, write down dx2. Let me put semicolon in here, and right here the diff of w to x, and the result will be 0. Why the result will be 0 is this: because the first derivative is out of x, so it's constant with respect to x, so the next derivative will be 0. Whereas if I am calculating the derivative, let's say with respect to a, the second derivative with respect to a, it will be something like this. Let's call it a, and I'm doing the derivative with respect to a. The first derivative, sorry, no semicolon. The first derivative is 2x cosine 2a, so I still have a. If I take second derivative, I will see another function. So I can calculate the second, the third, to the nth derivative. Now we have seen the derivative. We have seen how we can calculate the limit. We have seen how we can evaluate a value inside the functions with symbolic function that we have defined. Now let's see how we can do the integral. In order to do the integral, let's call it ix. I want to see the integral of, and in order to find the integral, I use the int. The function y that we had, let's say, y we had, with respect to x, and if I run it, it tells me that it is cosine integral of the x. let's have a simpler function. Let's see, w with respect to x, which is x squared sine 2 multiplied by a divided by 2 plus cosine b divided by 2. So and x squared has been multiplied by all of it. Now we can actually calculate this integral as we have done, and we can see what is the value, let's say if x is between -1 and 1. And if I do so, it tells me that the result is 0. Let's see if it is between -1 and 2. And it says that the result is as it is in here. Now, the last thing that we want to talk on today's lecture is talking about the Jacobian matrix. You know, the Jacobian matrix is a type of matrix that you would put the function on the first row and the derivatives comes on the second row. Now what I want to do is I'm clearing all the variable symbols that we had, and I define the new symbols, and let's say x, y, z, a, b, c, d, and I am defining x to be a plus 2b plus c, y to be 3a plus b plus 4d, z to be c minus 3, let's say a plus 2d. Now I have my x, y, and z defined. Now I am defining the Jacobian matrix, let's say Jm, to be, the comment is Jacobian, and the way that I'm writing it is in this form: x, y, and z, comma, the derivatives are respect to a, b, c, and d. And if I run it, what I will get is this. Look, the derivative of x, so look here, the first row is x, the second row is y, the third row is z. Then the first column is derivative with respect to a, second column derivative with respect to b, and the third column the derivative with respect to c, and the fourth column derivative with respect to d. The derivative here with respect to a is 1, with respect to b is 2, with respect to c is 1, with respect to d is 0. In other words, if here we had, let's say, a s squared, and here let's say we have c multiplied by d, and if I'm running it, we will see that the derivative of this respect to a is 2a, the rest is 0. When we come to, let's say, cd, the derivative with respect to c is d, the derivative with respect to d is c. And this is how we see the Jacobian of set of functions. Let's define do another example. Let's again clear all the variables and define the new symbols. Let's say we have r, s, t, and we say that x is, and also sorry, we have, let's say, x, y, and z, and we say that x is equal to r cosine s multiplied by cosine t, y is r multiplied by cosine s multiplied by sine t, and z is equal to r multiplied by sine t. And then this was, let's say, the first one. The second one, the Jacobian matrix, is Jacobian of, let's say, for x and y and z, and the derivatives are first one with r, then s, then t. And if I run it, I will get a bit more complicated and bigger matrix. For instance, in the third row, we don't have any derivative with respect to s because we don't have any s, so the result is 0, and so on. Of course, you can play a lot with this Jacobian. You can calculate the Jacobian and give a value by using the eval and see the numerical number for this Jacobian matrix. I hope that you enjoyed today's lecture. Be seeing you in the next lecture.